Hello folks, and welcome to the second part of this series of videos about Zcash and light wallets. If you didn't see the first one, it's on my channel, and where is it? It's this guy here, right? So what we left off was I think at the nullifier and encrypted node part. Sorry. We can have a short recap, just in case you didn't see the first video. So in this video, we said that essentially the Zcash transaction model is very similar to Bitcoin, in the sense that transactions simply contain inputs and outputs, and the outputs are nodes. So a node is basically the same as a check, and most important thing in that is that you have an amount and an owner. So forgetting about the owner, which in most of the case would be you, because you don't really care about other people's money. The remaining only important thing is the amount, and each node can have a different amount. So a transaction will take a bunch of nodes that you own and spend them. So it's either spend or not spend. You don't have a situation where you can take a node and spend half of it. So you either take it or you don't take it. So then you collect transaction will collect a series of nodes, and then you create a series of new nodes, new outputs, which typically would have a different owner. If for example you want to pay somebody 1 Zec, but your inputs, the nodes that you currently own, do not sum up to exactly that amount, you can just create two outputs, one of 1 Zec, and the second one will send the money back, the change back to your own account. So that's the same thing in Bitcoin. The difference with Zcash is that the nodes are encrypted. So we talked about that, and it's encrypted in a way that you are the only person who can decrypt it, and also the encrypted node, the encrypted output, is not identifiable beforehand. So in order to see the nodes that you have received, you must try to decrypt everything, and if you're successful with decrypting using your own key, it means that the node was yours. So outputs are in a sense not very different from the way Bitcoin works, except for that encryption. The other thing we said was that you have two keys for identifying decrypting a node. So not about spending, but just identifying the content of the node for therefore decryption. You can decrypt with your incoming viewing key, IBK. I'm just going to pull the protocol spec like yesterday. Where is it? This one. So you can decrypt with your incoming viewing key. Or you can decrypt with your outgoing viewing key. So the person who receives the node will decrypt with his incoming viewing key, and the person who sends the node can decrypt with the outgoing viewing key. So the keys will not belong to the same person. OVK would belong to the sender, and IBK would belong to the receiver. So that's about the outputs. For the inputs, it's also a bit different from Bitcoin, because in Bitcoin you can simply identify a node that you want to spend by giving the transaction ID and the position of the node in the transaction. Sorry. For Zcash, we don't want to be able to to tell which node was used. Even if the node is encrypted, knowing which transaction it comes from gives too much information. So instead, they use nullifiers. And the idea is that the nullifier is somewhat associated to a node, but in a hidden way. So if you know a nullifier, you would not be able to know which node was used. And the mapping is such that if you create a second nullifier, it would actually have the same value. So let's put it the other way. You cannot create a second nullifier from a single node. So even if somebody cannot identify which node was spent, if he keeps track of all the nullifiers, he can detect double spend, because if you want to spend the same node again, you would have to create a nullifier, and the nullifier would already have been published on the network. So there's like one node, one nullifier mapping, and that's pretty much it for that. There's a proof that of course you have to provide the Zcash dark. So, but we are not going to go into the details of how this Zcash dark is generated. The Zcash dark is there to prove that the nullifier that you have provided is actually the right one from one of the nodes. Right? So you as a guy who wants to spend something, you should know. Of course, you should know the node that you're spending. And that information will then be sent to the Zcash circuit, so the Zcash function that produces the proof. But once you have the proof, the person can verify that yes, indeed, a node from the tree was used, but he would not be able to know which one. That's the zero knowledge part. So you're proving that yes, indeed, you know which node it is that you're spending, but the receiver doesn't know which one it is. Right. So that's it. This is where we left off, and now we continue with the next part, which will be more about how to what are the exact inputs to this Zcash dark generation function. And in more in general, what information you need in order to make a spend. So there are a couple of things, of course, right? There's you need to know the destination, and you need to know the nodes and have the signature matching these nodes. But before we get there, I think it would be good to kind of anchor our discussion about these concepts and how they relate to the keys. So there's a very useful diagram here, right? And this diagram, let me zoom in, shows shows what's the spending key. So we have different version of it. For Sapling, the one we're currently at, this is the diagram. The Archer one is a bit different, but it's I haven't actually reviewed this one yet, so I don't really know how this works. And Sprout is obsolete. It's not used too much anymore. So let's look at this one. This is Sapling. So you start with a spending key, right? And so this spending key you can either generate it randomly, but most of the time these days we use a derivation scheme. So that's why you can keep a single seed phrase, which is like 24 words, and from these words and particular algorithm, we can get these keys, and we can get as many of these keys as we want. So and the process is not reversible. So if you have the spending key, even if you have thousands of them that come from the same seed, you will still not be able to know the seed. So there's a step here that is missing because it's not very relevant to sapling. But know that from the seed you can get the spending key. So these arrows means that there's a way to get the information downstream. So from S key you can get OVK and you can get ASK and so on, but you can't go backwards, meaning that if you have the OVK, you can't get the SK. So first thing here is what they call the expanded spending key. So you take the spending key and you derive three sub keys out of it. This part here, ASK and AK, so the old AK stuff, is for authentication, and this is what's going to be used to provide the signature on your node, on your transaction and on your node transaction. Well, on your spend, sorry. So we don't really need to talk about that. We just need that when we create a spend, we're going to have to provide ASK. And then you have also a path here, NSK, NK, which is the nullifiers. So the trick here, right, is that the nullifiers come from, so you will be able to generate a lot of nullifiers, and they come from your spending key. So somehow, I mean, it would be I hope more clear later, but let's remember that your nullifier key is baked, it's coming from the spending key, and it's baked into the IBK, because you can see that AK and NK are inputs to the IBK. So if you and then it goes back to the further down to the this is like the address, right? So you can see that with the different diversifier, we can generate a different address. So this is how you can create tons of different addresses that refer to the same account. This IBK is your account. So the guy who sends you a transaction only knows this part, right? He only knows the green part. So therefore, you will not be able to see any other transactions that were paid to you, to this account, because he doesn't have the IBK. He cannot reverse his operation. And because he doesn't have this IBK, he will not be able to decrypt your incoming transaction, incoming node. So, but because it's baked here, right? This NK will be used to derive the nullifier. So the trick here that we didn't talk about. So we talked about how we can identify the incoming transactions, so your incoming money coming to your account. But we didn't say how we can detect money going out, right? Because basically we can see a bunch of nullifiers going through the network on the blockchain. Every transaction will have inputs that have nullifiers. But without prior knowledge, we can't tell if this nullifier is from one of the nodes we have received, or it's somebody else's nullifier. So the way it works actually is that if you have this path, if you have this NSK, NK. Well, actually, you don't need NSK. You just need the NK. You can calculate in advance what nullifier would be used when we spend the node. So that's kind of the trick here. If you have the IBK, you can only detect incoming money. But if you have the full viewing key, which is the IBK, but also with OVK. Alright, so it's not only IBK, right? It's AK and K. AK and K derives IBK, and you have OVK. So this is really like IBK, OVK, but IBK broken apart. We have AK, NK, and AVK, OVK. AK we don't need for this purpose, but we need NK and OV. Essentially, we need NK and IBK. So the full viewing key will give you this information. And to detect spans, for each node that you receive, you would pre-calculate basically the nullifier, right? So you know the NK, and then will be an algorithm for that. You derive the nullifier, and you store the nullifier along with the node. Again, that's only possible if you have this part. If you only have IVK, you can't. Then the rest becomes easy. When you spend it, then you will see that the nullifier matches one of the nullifier from your database. So that's pretty much it, right? The process of detecting spans is scan the blockchain, take every output, try to decrypt it if it's with your IVK. If you can decrypt it, then you store the node inside the database. And then at the same time, you use your NK to derive the nullifier in advance. So you put the nullifier along with the node that you decrypted in your database. And then if at a later time you are spanning that node, then the nullifier would be the one that you have stored in advance, right? So this algorithm, you use it if you're, for example, if you're scanning the blockchain and you want to restore from a seed. If you are making a transaction and you're spending at this time, you obviously know that you're spending a particular node, and you can mark that node as spent right away. But if you are recovering an account, then you don't have, you have to use the algorithm I just described. So that's pretty simple when you think about it. And now we can move on to the to the next part of this, which is about actually what is the information that you need in order to spend. Right. So we have already covered how we received, which was pretty simple. You just need to give this address, this green part. We know how we just described how we can calculate the balance, because we can detect incoming money, and then we can detect outgoing money. So receiving nodes and spending. Just by doing the difference, you know your account balance. Now the last part is how you make how you spend, how you create output transaction. So one part of the output transaction we already know, which is the encoding of the output node. Right? We talked about this a bit earlier. So now the only thing is we need to create the nullifier, create a nullifier, and also we need to create the Zcash knock, the proof. So the one way to see this is we can look at the protocol spec. Let's see if it's described here. Okay, not sure. I mean, it must be somewhere, but I don't remember. Okay, so I think the one that is that we need is this guy. All right, so okay, it's a bit complicated. I mean, if you're not used to it, I guess. So the most difficult one is this part here, the Merkle path validity. All right, so before we get to explain what this means, we need to remember the stuff with the nullifiers. So the nullifiers, so you need to store them. Okay, so that's a given. But as a light wallet, you don't really have to, because you assume that the full validating node that you're connecting to is already taking care of this validation. So it will reject any double spend. So you don't really care about the nullifier. You can assume that this is already correct. But when you make a spend, what the protocol needs is this guy here, right? And this guy is based on the node commitments. So when you make once people make a new node in the output of a transaction, there's the a node commitment, which is basically very roughly a hash on the node. All right, so let's see if they say exactly what it is. Node commitment trees. Output. Yeah, so we said about that. An output transfer creates a node new, and it contains a value commitment. So that's about the amount on the node, and that's used to ensure that the node is not the sum of the outputs is not bigger than the inputs. So there's a statement for that, and okay. I think it's not in this particular page. Give me a second. Well, it's okay. It's somewhere. It's actually this guy, this CM here. It's RCM. No, if I'm not talking about, is it? No, maybe not. There's a page where they describe the format of the output. So, well, I can't find it anymore, but what I was looking for is in the protocol, you have the blockchain format, like how the bytes are laid out, and you have the layout of a transaction. Then you have the layout of the inputs and the outputs, the spends and the outputs. In the outputs, you see that there are several fields, and one of the field is the node commitment. So basically, what I'm trying to say is that by looking at the blockchain, you don't get the node in plain form, obviously, because they're encrypted, but you get a commitment, which is kind of like a hash computed on the node. So this is what you need to store here. So all these node commitments, if you are full node, you're supposed to store them all. So, and earlier we said that we did store them in a list. So that's only half true. We do store as a list in the sense that they are appended, they are one after the other, and then we never shuffle them. So the first node commitment we receive would be at index 0, the second one index 1, and then we continue. And we never change the order. So we always add the node at the end, new node at the end. But it's not a list, it's not strictly a list. There's actually a more complex structure applied on it, which is described here. So you see at the bottom, these nodes the node commitments are as leaves of a tree. And then basically what happens is that 2 by 2 they are combined. So these are hashes, and therefore, well, anything can be hashed together, right? So if you have 2 series of bytes here, any series of bytes can be hashed. So this is a series of bytes, this is a series of bytes. We can put them one after the other and make a series of bytes, a sequence of bytes twice as long, and then hash the result. So that's what happens. We take these two guys, we concatenate them, and then we hash the result. So that would be the content of this box. Same thing for these two. We get the content of this box, and so and then these two, this box. Then these two guys are then recursively combined. So we combine these two together to get this one, and so we continue until we reach a single element, and we stop there. If the number of nodes is not even, sorry, then you can see that this node, for example, CN4, which is the fifth node, doesn't have a partner, they have a sibling. In this case, this is pick a placeholder. We pick a series of bytes that are arbitrary. Well, it's a ref. It cannot be like any series of bytes, but it's a series of bytes we know in advance. And then we use that as a placeholder to combine these two together. And the same thing happened here. We use another series of bytes here, and then we combine, right? So unless the number of nodes is exactly a power of 2, this usage of placeholders will happen somewhere. So at the end, you have a node, a root, and that root is actually published in the block. So this data structure is very important, because if a node is changed in any way, if you have even one bit swapped, flipped anywhere, the hash at the top will be completely different, because you can see that if you change this one will change. If this one changes, this one changes, and then eventually the root will change, because somehow every node has a path to the root. And the path means that every node is somewhat involved in the hashing to reach the root of the tree. So, for example, if we were stopping here, right, and we are changing this node, then that value will not change, because the path from here does not intersect this node. We go this way, and we never use that particular input in any of the hashes that are involved in calculating this value. So that's a very important data structure, because every time you make a span, you need to give part of the algorithm for the statement that the Zcash narc establishes as true. Involves this path. Right? So you're basically saying that you know the position of your node that you're spanning, and you giving the Merkle path, this path, which is called a Merkle path, and that the Merkle path, the root guy, is one of the root of a block. Right? So you don't really. You have to say which anchor. So you need to say that you're spanning a node that exists as of block XYZ. But you would not say which one of these nodes you're actually spanning. But you are in order to produce the statement, you need to give that path. And actually, the path that you're giving, to be exactly precise, is not the path. It's not exactly these values here, right? It's not these values here, but these are the values that you need to provide in order to calculate these values. So let's take a step back and see what I mean by that. So if you provide, let's talk about CM2, right? So if you have CM2, and you see that CM2 and CM3 are combined to get this one, then if I give CM3, a verifier can recompute CM2, CM3 hash together, so he can recompute this value, right? But then he will not be able to compute this value, right? So because he doesn't have CM0 and CM1. So one brutal way is to say, okay, fine, I'll give you also CM0 and CM1, and then you can compute this one, and then you can compute this one. The goal here is to verify that you didn't cheat, right? That you actually know that you didn't change CM2. Right, so that CM2 is really a part of your tree. It's really one part of your list here. So if you want to prove that you didn't change CM2, you could, and you know the guy who verifies knows the hash at the top. One super brutal way is to give everything, because CM0, CM1, CM2, you give all the nodes again, and then sure, the verifier can combine rebuild the tree as you did, and check that the result at the root is the one that he expects, and the one that he expects is part of the block header. So it's something that we have proof of work on, so but nobody can change that. But that's extremely wasteful. You are resending everything. Much smarter way, and this is the reason why this data structure is built. Sorry for the beeps. Is to only provide the information along the path to the root, but on the other side. So CM2, I give CM3. Right, so I give CM2 and CM3. CM2 is the one I want to show that I know. Right, so I give CM2 and CM3, and you hash them together, you get this value. Now, if I lie to you and I change CM2 or I change CM3, this hash will be different because I'm not capable of finding a new source, a new input that hashes the same value. So I just can't find another CM3 prime, such as CM2 prime and CM3 prime combined to the same thing as CM2 and CM3. So that's an assumption that we are making. So the only way for me to get the same value here is to give you the right CM3, right? And likewise here, in order to give the right value here, I would be forced to give you the right value for this one, right? So it assumes that the sender has a whole tree, and the verifier only receives the nodes, the hashes that are needed to progress further up the tree. So for this level 0, I would need CM3. For level 1, this level, I would need this one. And then for level 2, this level, I would need this one. So it's always a sibling, the other guy. And you notice that if I'm here, right, if I'm talking about CM4, then I don't really need anything because I just need to tell you that I'm on level 0 and that root is on level 2 and I have no sibling. So you would use the placeholder value, you would hash them together, and then you will use the second placeholder value and you hash them together. And then at this level here, I would need the sibling that is on this side. So I don't give you anything, but I give you this one here. And then you can hash this one and this one to get the root. And you can see that along the way, if the sender lies or provides a wrong value for the node on for any of the nodes, the error will cascade. Right? He will cascade up to the root, where basically there's no more information to lie about, because this one is obtained off band, is obtained from the block header. So this will be different. Okay, so it's a very long explanation, but I hope it was helpful and you understand why we do this stuff. The why is not super important. It's more than the fact that we have to do it. And the biggest part of the biggest problem of the Light wallet is related to this tree. This accounts for 90% of the computation requirements of a Light wallet. Finding transaction, okay, not talking about actually the spend, because let's continue why this is so painful. The thing is here that this tree would change every time you receive a new node. not even receive, every time a new node is sent to the blockchain. So not necessarily your node, and most of the time it will not be your nodes. Every time somebody makes a transaction and makes one output, you will have one output here. And each transaction will have several outputs, so you will actually have several nodes added here. And whenever a node is added, you can see that the part of the tree, but at least the root would change, and part of the tree would change. So this part of the tree would change. This part of the tree would not change, right? But you can be sure that the root would be different. And when you want to spend, so I suppose, for example, I want to spend this one. This was my node. There will be a ton of other CM4, CM5, CM6. All these nodes will appear here, and these nodes will somewhat change my path. Sometimes it doesn't change that much. Because, for example, if I add stuff here, this hash would change, right? So when I give the Merkle path for my node, I will have to give this value here, and this value would change. Right? So that means that in some way, every time a new node appears on is published, the information I need to keep track of for my spends is also changing. So this is the current implementation in Libera's Zcash. It will update. So this is called the witness, the sapling witness. So every time a node is added, the current implementation in Libera's Zcash will update the witness information for every node that I own, right? And that update takes a while, because these hashes take some time to calculate. And also there's also another thing is that for Light Wallet, we don't want to keep CM0, CM2, CM3, CM4, right? We only want to keep CM1. Ideally, we will only want to keep CM1 and our sapling witness. But you can see that we need to be crafty, because if I don't keep anything, if I only keep this path here, and now I receive CM5, I would not know how CM5 impacts my path, the path of CM1. So intuitively, we can sense that there's some additional information required in order to maintain the sapling witness for CM1. So intuitively, we can see that just keeping the sapling witness for CM1 is not going to be enough in order to update these witnesses when new nodes are coming. Of course, and that's going to be the topic of the subsequent chats. How do we? What information do we need to capture, and how do we make this calculation as lightweight as possible? Because we have a sense that updating all our witnesses, because we probably have more than one node, right? If we have 100 nodes, we're gonna have to update with this 100 path every time there's a new node that arrives. So intuitively, it sounds like very expensive. But that's the key problem. So I think I will leave you at this point, and then continue later with more details on how this stuff is calculated, and how we can make the calculation lighter. So the next one will even be more technical, and because we're going to dive into how what data we need to keep track of, and how this data is modified. So these are going to be the actual algorithms and the data structures required to keep this kind of tree in either in memory or in database. So here, I think we make a lot of progress on this today, and this is a very, for me, it was very hard to grasp, and WarpSync is mostly 99% about this guy, because again, the profiler gave us that this is where 99% of the time is spent. So to close, you also need to know that if you don't need it to spend, if your account is only based on the viewing key and you just need to detect your balance, to calculate your balance, so you just need to detect incoming and outgoing transactions, the problem is 100 times easier, right? You don't need to keep that at all, or you can just ignore it and you never calculate any witness because you're not going to spend anything anyways. So if you have a wallet that says it's really fast, but then it's really fast in calculating and getting you the account balance, you should ask more questions, right? Because we can see that contrary to other currencies, the problem of spending is much harder than the problem of getting the balance. And therefore, having the correct balance on the screen may not be sufficient for spending, or it's not sufficient for spending. And what I mean is that maybe the wallet is showing you the balance, but it's not going to be able to spend this entire balance. So it's possible that the wallet computes these guys in the background, and that eventually these witnesses will be ready. But it's also possible that it's all already calculated and the wallet is entirely 100% ready for spending. And if you have a wallet that is only based on the viewing key, a simple optimization is to discard all this knowledge, right? Never calculate that. But you do need to calculate that if your wallet can spend eventually. So even, for example, if you have only a viewing key, but you want to be able to create unsigned transactions for signature offline, right? So your online wallet does not have the full secret key. It only has a viewing key, but you need to be able to prepare the transaction for offline signing. Then yes, you have to also maintain this guy, right? So to be more exact though, it's not because your account is IVK that you don't have to calculate that. You can calculate that even though this is only a watch-only account. But you don't need to calculate that if you're 100% sure that your account is never going to be used for spending. So that's kind of like the difference between Zeg wallet and Z wallet and also Nighthawk. Z wallet calculates this guy in any case, because your watch only accounts can be used for spending using the cold wallet feature, where you create an unsigned transaction, you export it to a USB drive, then you sign it on an offline computer, and you bring back the signed transaction, the fully signed transaction to the online Z wallet, to your mobile Z wallet, and you use it to broadcast the raw transaction. So because we have this workflow in Z wallet, we need to calculate all this stuff, right? We need to calculate the Sapling witnesses, and WarpSync is not going to differentiate between account balance state and Sapling witness state. When you see when we show the blockchain has been fully synced, it's because we have calculated both account balances and the required Sapling witnesses. So that's the difference between Z wallet and Zeg wallet. Zeg wallet will do some background calculation, and they decouple the account balances from the Sapling witnesses. Okay, so that's just a small parenthesis in case you wonder about the performance profile of these different wallets. They don't do exactly the same thing, and the result will be obviously implementation is also very different. So they don't even do the same way, right? The calculation of this stuff is not going to be the same. The output, the result will be the same because for creating the signature, creating the Zk snark, you will have to give that path, and you have to give the same path. So regardless of how you maintain and calculate this tree, the input to the Zk snark proving function is going to be the same, right? And this is all about optimizing this tree. All right, so I'm really going to stop here, and the next chat will be about how Rust Zcash maintains this tree and how WarpSync maintains this tree. All right, okay, so thank you for listening, and I'll see you soon.